this is a fun lecture. I'm really excited to teach you guys how to make your own functions today. We've been using functions from other people. We've been using functions that other people made for us. But wouldn't it be nice to make our own, right? To give a name to some idea and have that be our thing, some code that we write that we can run as much as we want because we've given it a name. That's all a function is. It's code that you've given a name to that you can just call and call and call again. Let's make our own. All right, this is chapter 8 stuff, so please start that one. And yeah, bless you. Please do that. Attendance, it's still running, and let's get started. So let me teach you how to make a function. So we've been using functions. Let's make them in Python now. So this is the Python way to make a function over on the right, very simple one. Let me try to show you all the different pieces that you need in order to make a function. All right, so this is a very silly function. It's a simple one. It's called double. It's meant to give back 2 times the input number. It's called double. It takes some number x, and then it gives back 2 times x. So like the goal of the double function is like you call it like this, double 5, and it like gives back to you 10. Okay, so that's what that function is doing. I'm going to try to explain that to us. So like that's a simple kind of function that you can make yourself. All right. So all right, the very first line. The way it works, to make a function, you have to say def, like I'm defining a function. Def for I'm defining it. And then you give its name, and then you kind of give how it's going to be called, but you use a variable. That's called the signature of the function, this part right here. It's called the signature. That's what it's signing its name. So it's got its name, and it's also got what it takes as a variable name. All right? So like you're going to give 5, then that 5 is going to be plugged into this secret variable called x. All right, double is going to take something called x. Okay, and then you do a colon, and then you indent, and all the code that you've indented by like some spaces or like a tab. Usually the editor will do it for you. So like Jupyter, when you just press enter, it'll probably indent for you. But as long as you're consistent, you got to keep them all on the same level, because the second you unindent, you're done with the function definition. That's kind of the idea. So like everything that's indented is part of the code that runs whenever the function gets called. And yeah, the very first line usually of a function is a triple quoted string. It could, you know that can be many lines long. It's a special kind of string that could have enters in it. I'll show you that in a second. But the very first thing you can do in your function is give a description of it. That's called a doc string. All right. So the very first line of your code isn't really a line of actual code. It's like a description. It's a comment of what's going to happen when you run this function. It's called a doc string, short for documentation string. And that's what you get back, actually, whenever you ask the name of the function and a question mark in the Jupyter cell. So if you say, after you define this, if you were to say double question mark, it would print out the doc string. And that's what we've been using to tell us about some things like table underscore read table question mark. That is a very long doc string of the function. All right, that's a multi-line one for sure. But that was at the start of the definition of that function. If we go to where this was written, we'll find that there. All right, so that's what that does for us. That's the doc string. It gives you back to you whenever you ask for the name of it with a question mark. And then this whole indented section, all the code that belongs to your function that you're defining, is called the body of the function. We call this the body. I guess the reason is because like this is like the definition top part is like the head, like the meat of the function is where stuff is going on. That's the body of it, we say. And yeah, the only real code line of this function is return 2 times x. And what that means is first do 2 times x, and then give back the answer of that. So return is a statement that gives back a value to whoever called you. The second you say return and then something, that something is being sent back to whoever called the function, and then the function is over. All right. The second it finds a return to go down, that ends the function. It gives the answer back that you're returning back to whoever called the function. We call that the caller, all right? The caller of the function. And so what happens kind of is this variable is important. We're going to get to that more in a second. But kind of here's the deal. Let me kind of draw what happens if we were to call double, not with 5, but like 42, all right? So here's the secret, because you know it's going to give back, the goal is for it to give back 84, right? It's going to result in 84, 42 times 2. But the way it works is the second you call double of 42, that 42 goes up to here, that variable. It's like that x is a variable that exists for the duration of the call of this function. It's like it's a variable that exists as you call it. The x gets set, because it's just a variable, to whatever you passed along. So that's a way of setting a variable for it. At the very start, before the function gets called, that 42 goes into x. And now, the reason it's a variable is because it's like whatever you got given, work with it. It gets the 42, it exists, and then you use it and you return, and then the x kind of belong to the function, it goes away. So that's what that's called. This is called a parameter of the function, right? So your argument 42 goes into this. It's called a parameter. It's just a variable for the life of the function call. So really, when you call double 5, that x variable is being set to 5. That's how it knows to double that number. That's whatever you were given. So there's going to be an x variable that gets made for the duration of that call, and 5 gets plopped into x there. And that's why 2 times x makes sense, because it's going to get this value, right? It makes 10 out of that, and it returns the value back to whoever asked for it, all right? So that, in a nutshell, is how functions work. You say its name, you say what it takes as variable names, because then when you actually give something, give real arguments, they get set into this variable, and then you can work with those as you do your computations. Are there any questions about this double function definition and how it's going to work when we call it? Does that make enough sense for now? So I want to do this in code too, but I want this kind of all these terms to make enough sense at the start. Because that's the trick. You can have as many lines as you want in the body of your function, as much fancy lines of code as you need to do whatever you're trying to do, and you go from there. So here, instead of double, for fun, let's make another kind of function. Let's do let's make a function called, instead of double, quadruple. Def. You say, all right, I'm making a function. Here's kind of how I want to use it, right? I want to make a function that works like this. If I were to say quadruple of 42, it would give me back 42 times 4. That's the function I want to write right now, all right? So to make it, I say def, give its name, quadruple, and then you give whatever it's going to take. How many things is it going to take? It's going to take one thing, like the 42, the thing you're asking to quadruple, and you give space for that as a variable name. So let's call it, instead of x, we'll call it y. So quadruple of some y value, you're going to get that every time it's called. And then colon, like here it is, here's what we do when we want to quadruple something. It just indented for me. And so you give a triple quoted string, that's your doc string, customarily at least. You can omit that if you're lazy, and I will usually be lazy as I'm teaching. But all right, what does this do? It quadruples y. Oops, if I can spell quadruple the y value, all right? And so how do we give back an answer? What do we give back? We were given some value in y, like the 42. It could be something else. I could say 43 instead, right? Whatever it was, it goes into y. How do I want to give back an answer with y? I want to do 4 times y, don't I? That's what the idea of quadrupling, and I want to give that back to whoever called me, and the magical incantation to do that is you say return whatever that result is that you want to give back. So it's really just a one-line function. But now if I run the cell, it exists, and I can call it as much as I want. So this will give back 42 times 4, that's 160. That's pretty cool. Are there any questions about that? Do you see it? The return is important. The return gives something back. If I just said 4 times y, this gives back nothing anymore. This gives back nothing now. It's completely emptiness. When I press Shift-Enter right now, I get nothing back because I never said return. Return gives something back. So you needed that. Okay? And then, yeah, this doc string is what you get back when you ask about your function. Oops. So if I said quadruple, question mark, it will give me back the doc string properly eventually. Oh, there it is, yeah. It's so short. I found it, so I couldn't find it. There it is, quadruple y. We see it there when we ask about it. We could have said more things. We could have put more things on more lines, but that's a good start. Right? And that's what quadruple does. It can take, the whole point of a function is you can call it multiple times, so you can give it more things that get placed into this y variable. So like quadruple 3.14. Anything that you could star with, right? Do 4 times with. It's fine. Remember that you could multiply a string, a str, text by a number. Remember you could do that? You could do like 2 times, or like 42 times high, and that makes 42 highs. So that code works for quadruple still. If I said quadruple, I could say, hi mom, and it will quadruple that. It's still fine. Anything that you can do 4 times with, it'll work. Isn't that cool? So that's another example of that function, and you can call it as many times, and it just jumps up to here with whatever you call, like 3.14, gets placed into this variable, and then it runs all these lines that are indented, and it gives back an answer whenever you say return. It does the math first, and then it returns that answer back. Do you see it? Questions about that? Because that's really powerful. That's the start of a lot of cool stuff now. All right. One thing I do want to say is this is a variable y. We're using it inside this function, but it's local to that function. We say it only exists for the life of the function call. So if I were to ask about y right now, y, shift enter, it will say y is not defined, and that should make sense. It only exists for the life of this function. It makes no sense to talk about y any other place because like y changes as we call the function, right? Y gets to be 42 this first time, y gets to be 3.14 the second time, y gets to be hi mom the third time. Like, there's no point in keeping track of some y outside. It's only usable. It only makes sense to ask about y in the function because that's what you provided. Okay? I think that's what I wanted to say. So yeah, questions about that? Yes? Oh yeah, it doesn't run it. It doesn't run it. It's just there. That's just for the docstring part. So it's not real code that actually runs for us. But you could put multiple lines and do other things. You could be like, I don't know, answer equals 4 times y, and then return answer. Like, you could have multiple lines. But the result of running the string, it doesn't do anything. Yeah, that's a good question. So you could put as long of a string as you want, and it doesn't like change the computational time that it takes to execute the function. Where? Oh, sure. Let's try that here. Let me go back to how it was. Yeah, definitely. The beauty of all this is we could try every question out now. So like give 2 things like here. Yeah, that's a great question. It's going to give me an error because the way we created quadruple is we said it took this one thing in y, and that's kind of like the template for how to call it. And so we didn't give a second thing, and so we can't give a second thing when we call it. It'll get confused. Does that make sense? Yeah, that's a great question. So it says it takes 1 argument, but 2 are given. Sorry, it doesn't work like that. If we wanted a function that took multiple things, we could say like y comma z, and now we have that thing. And that would force us to use it now, too. That's a cool idea, and we'll get to that. Great. Any other questions before I give you a question? These are good ones. So yeah, let's play around with functions. We're going to write our own. It's very, very powerful, very cool. All right, here's my question for you now. Here is another function, and I want you to think about it. So, gosh, I think I'd rather just you think about it in your head. You don't have to write this down anywhere. If you want to get together in a group, I would encourage it. Talk to each other. But here's like a secret function. It's just called f. It takes something called s when you call it, and it runs these lines, and it gives back this answer. I have to remember what all these functions do. My question for you is, think about this. What does this function do? If you call f on something, what's it going to give back? What's it trying to do here? What do those lines mean? First of all, if like remember what all that stuff does, look in our documentation. What kind of input does it take? Because it can't just take a number. If you think about it, like you can't be like sum of 42. That doesn't make sense. What kinds of things does sum accept? Because that's the first thing you do. What does np.round do? Because like you're doing s divided by something. What does it need? What kinds of things can go in this s? What kinds of things can you call f with? This is a harder question, so don't worry if you're scratching your head. But I want you to at least think about it for a while before I show you. And then also think about what is the output? What will it give back? Because when you say return, whatever this is the final result of the function. What is it? What do you think that means? And then my final question for you to ponder on your own for a little bit is what is a good name for this function? Because f was not very descriptive, right? What should we call this? Because you can call it any name that you'd like to call it. What would be most appropriate? All right. So yeah, think about that for a second. Let me know if you have any questions about it, but just ponder that in your mind. What do you think this function will do? If you have time, maybe type it out. Try running it, because it won't give you errors if you follow it correctly. What is it going to be? Yeah, it's not a good enough name, that's for sure. My hint is like, what does sum take? What are you summing up? It's got to be multiple things, right? So it's going to take a sequence of things, won't it? What's our word for that in Python? Yeah, try it out. I'll give you a minute or two more, and then I'll show you how I want to think about it. Oh, did I miss it? So yeah, it's going to take an array. An array of what is the next question? And then what does it do with that array? Mm-hmm. All right. Yay. All right, I think I did the right thing. All right, what are our thoughts? What do we think this function does? Did we try it out? Any ideas? So I can try it out too. What kinds of things does it take? Like it'll take an array. Is it an array of strings? We'll work with those. Probably not, right? So one thing I could show you is some functions can take a bunch of different things. Like quadruple, it took 3.14, it took 42. Like that was an int, that was a float, that was a stir. It also could have taken an array even. Like quadruple 4 times an array totally works out. It'll just multiply every value of that array by 4, wouldn't it? So I could have done this. Quadruple of make array 4, 5, 6. And it will give me 16, 20, 24, which makes sense. So quadruple works on a lot of different things. F doesn't quite work on all the things that it should. All right. So, all right, let's think about F. What's it going to take? I think it's going to take a bunch of numbers, right? It doesn't have to be ints, but for example, let's say it could take 1, then 2, then 3, because that's the kind of thing you'd sum up, right? And it would make sense to sum up numbers. A sequence of numbers is what F needs, so S is maybe for sequence. Oh, did I lose the internet again? Oh, they must be messing with the internet in the room right now. Oh well. So yeah, that's the kind of thing that F could take. And yeah, then what would happen when this code got run? We'd say we call F with this value, for example. That's what S is. Let's say that's what S is when we call it. Like let's say we call F with make array. Oops. I guess the internet came back from my computer. Make array of like 1, 2, 3. The second I call it like that, S gets to be whatever I pass here. So S gets to hold that array. I'll draw it like that with the angle brackets. It's quicker for me. And then the very first line this code runs when we call it, right, is this total equals sum of S. So it makes a new variable just for that function call called total. And it's equal to the sum of whatever was in S. So we pass this particular sequence. So total will, for this call, be 6. But it's something different every time you call it, of course. And yeah. Then the next thing it does is it returns the result of doing all of this. And so we got to figure out what that's going to do. So, okay, it's going to round all these things, whatever's in this resulting array after doing this kind of math, by 2 decimal places. All right. So this function is doing rounding. This is 2 decimal places, and then this is the final answer. So, okay, it's going to take the original stuff. So S over total, so it's going to do, it's going to calculate 1 over 6, right? Because total is 6. So the very first element is 1 over 6. Does that make sense to us? Because it's going to do the array 1, 2, 3 divided by 6, because that's what total's holding right now. So it's 1/6, and then it's doing times 100 for all of this, isn't it? Times 1/6 times 100, and then it's 2/6 times 100. And then it's 3/6 times 100. Boop. And that's what it's giving back. All right. And then it's rounding whatever that answer is to 2 decimal places. What? Do we kind of see what it's doing? Are there any thoughts? In English, how could we specify? Like, what would the doc string of this function be? How would we describe what it's doing? Or its goal? You want to try running it maybe? Would that help? Because something interesting is happening. When you're dividing by a total, a bunch of values by a total, what are you getting? So there's F. And so I could call it with F of make array. Oh, sometimes when you paste from PowerPoint, it's unhappy. There we go. F make array, let's say 4, 5, 6. Or we were doing 1, 2, 3. Why not do that again? Looks like we get 16.67, 33.33, and 50. And these all add up to 100 because they're percentages. Does that make sense? So what this function is doing is it's converting these values, whatever they were, into like their weights. Like how much weight did the 3 carry? It was 50% of all the numbers here. How much weight did the 2 carry? It was 33% of all the value of all the numbers summed up here. How much weight did 1 carry? It was 16.67 of the total amount. And so that's kind of what F is doing. It's calculating like what is the relative percentage of all these values in the sequence. Does that make sense? So it's a useful function to do some things with, but F is probably not the greatest name. So let's call it something else. But do you see what it takes? And you can give it something else to confirm that. Like, all right, F, let's give it 20, 25, and 30. And we have something different that we result. We see that the 30 is 40% of all the data because it's calculated as 30 over the sum of that array, like, which is 20 plus 25 plus 30. That's what it's calculating, and it's multiplying it by 100, of course. That's 40%. The 30 was 40% of all those values there. And so that's what it's generating. And so F is like converting those numbers to the percentages, to their relative weights, to their relative percentages in that input sequence. All right. So that is kind of my idea of what it should be and what it's doing. Are there any questions about this function F? You kind of see it? So it's running multiple lines. It's given back an answer with the return, and it's happy. So let's give it that name. Instead of calling it F, let's say def, let's call it percents. And we'll give it some actual normal values. And so maybe like, instead of S, it's like, what are the, like, maybe you got like, I don't know, maybe these values here are like counts of things that you have. Like I've got 20 white socks, 25 black socks, and 30 blue socks or something. Like, all right, so the percentage of blue socks that I own is 40% of the total number of socks or something. Like maybe S could be, we could call that counts. And then once you say it like this, you have to use that everywhere, of course. So counts. And now I've called it percents. All right, so if I run it again, it's still happy. It's still doing the same stuff. But you can kind of see that it's a cleaner function now. It's got some normal names and things. And we could even give it a doc string with those triple quotes. That just describes, not actual code that runs, it just describes what this function is doing. We can say that it converts the values in counts to percents out of the total. And total was already a variable that we had, right? So that's an idea for a doc string. And doesn't have to have spaces around it. It could look like that. And so now if we were to ask percents question mark, we'd get back that doc string, and that would remind us what this function was doing. That's the point of putting it there. That's pretty cool. All right, I think that's what I wanted to say about that. Any questions about what I've done to this function before I extend it further? Like, I want to give it another argument, because we only got one thing here, the counts. What if I wanted to call percents with multiple things? How would I make that happen? That's where I want to go. All right, let me show that to you. So that's like the old version of percent. So let's do it more, because sometimes, right, when you're printing it out, like this is nice. This is we rounded it to 2 decimal places. But sometimes 2 decimal places isn't enough, or maybe it's too much, like we wanted a whole number. This comma 2, when we call np.round, is controlling how many decimal places we get. What if we're not like in a position to decide for the user of our function that it's 2 decimal places that they want? Because that kind of gives them less control. Well, we can deal with that with this by doing this, by taking this percents function and not just finishing it here, but like giving it another parameter. This is called a parameter. Have it take another argument, say how many decimal places you want it to round to. So that can be the next thing that you give. And now instead of 2, it's just whatever you got for decimal places. Does that make sense? We could do that. We could add another argument to the function. And this is called, when you do it in the definition, it's called a parameter. I'll try to make that distinction. And so now you can ask for how many decimal places you want when you're converting those percentages and rounding, because this will be passed right there to np.round, whatever you leave there as that second thing. So now the way you call the function changes. The way you call the function changes. Now if I say it like this, I could say like, all right, percents of all these values, but now I need to give that second thing right here. The first thing is the counts. Then the second thing is how many decimal places I want this rounded to. So let's say I want it rounded to 3 decimal places this time. So now when we get this output, isn't that beautiful? Now we get all these values rounded to 3 decimal places, because I passed that here, right? This 3 is going to be plopped into decimal places, that variable. And that will control the rounding at the end there. Because the user gives me 2 things now, and they have more control. Isn't that cool? So you can have as many arguments as you want to your function. You just got to put as many variables to accept them all. It's beautiful. All right. Though with that power, the user has more responsibilities now too. They have to give you those 2 things. What if like they really just wanted to not care and like by default have it be 2? It's like, all percents with the function with the sequence don't give a value for decimal places. The user can't do that right now. So we have forced their hand, right? We've added the second argument and made it necessary. It's saying percents is missing 1 required positional argument, decimal places. You forgot to give it here. You can't have both in this way right now. You can't have this control but also have a default unless you do something. So like that's the last thing I want to show you. So it is possible to make it so that this decimal places argument is optional. It's possible to let this function still have the total control by passing how many you really want, but if you forget to pass something, let it have like a default of 2 or something like that. That's the last place we can go, and that's called a default argument, all right, or a default parameter. And so the last thing, if we want to avoid this error and let there be a default, there's one last way we could define this function. We can say instead of counts, comma, decimal places, we can say, all right, take some counts, take some decimal places if the user wants to give them to you. But otherwise, by default, if they didn't give you them, use 2. That's what that's saying. By default, make it 2 if the user did not give you a second value here. That's called a default parameter. So that gives us the finest grain total control. If I were to define the function this way, with this default value here, this equals 2 for decimal places, Now I can call the function in the old way and the new way. And this can be the final definition of it. So I can still say percents by itself because I did not give a second thing. I only gave the first thing for counts. Decimal places is set to 2 and it runs with that 2 value. But if I want the full control, I can say, no, decimal places, I'm going to give you a real value, make it 3 this time. And then it will prefer your thing that you provided. It will cancel out the 2 and make it the 3 that you passed, and then use that for the final rounding. So you have the control as well as the defaults with this idea right here. With that equal sign, that gives you a default value for your parameter, for the argument that you pass. If you forget it, it'll just use the default. But if you provide it, it will use what you provided, of course. You've overridden it at that point. That's very powerful, and that's most of the ideas for functions that I wanted to tell you. So if that made enough sense, that's great. Are there any questions about this final version of the percents function? You see what it's doing? Very, very useful stuff. And remember, the idea of a function is you've given a name to a computation, to a bunch of lines that did something for you, so you can rerun it with like a new value, new values for your sequence, or your counts, or whatever. You can rerun it so that you don't have to like copy and paste all this code. You put it in one place, generalize it with the names of variables. Those become the things that you call the function with. That's very cool. All right. So the next place I want to go is combining this with our idea of tables. Like I want to run functions on values in our tables on all the data sets that we're using. Are we ready to go there? Because right now this is just functions on numbers and sequences that we make ourselves. But you better believe we could have gotten this array that we passed to percents out of a column of a table, right? So that's kind of where I want to go if we're ready. But yeah, feel free to derail me if you would like. That is my next goal. I would like to be able to do this. I want to apply a function to a table. All right. So let's make a section for that. Applying functions to tables with a capital T, of course, because that's what our library is calling them. So that's where I want to go. All right. So if you want to call your function on values in rows of a table, this is how you do it. You say you've got your table already, then you say .apply, then you say the name of your function, and then you give the labels or indices of the columns. You just comma separate as many as you need to input to your function. Because maybe you need like 2 values. Where are you going to get them from? Which columns? That's what it's saying. I just have to say these words before I give you an example. The example will make more sense, I know. So the first argument is the function you want to apply to each row of your table. And then everything you give after that is which labels or which indices of the columns that you want to use as input to your function. All right. So the documentation page can help a little bit there too. If we go there, either one of them. I like this one. So you got a table, you can say .apply, the name of your function, and as many columns as it needs to run on those things. So like you can apply baked-in functions as well, like the average to each column, and so we'll get to that. And that's where I want to go. So let's see here. Yeah, let's make that happen. This was kind of a silly thing to do there, but that's okay. Yeah, that's kind of how you call it, but let me show you a better example. So let's say, let me make a table. Let me make an easy table that's small. Here's a table of places that I came up with as an example. So blank table, let's add some columns. Let's add the first column being place. So here's a bunch of places. Here are their names. We got Fresno. We've got a very low place, which is, let's do Death Valley. Very low elevation. Let's do Shaver Lake. Very high elevation. So those are places, and then let me also store the elevations. That's where I'm going. Let's make this table. So what's the elevation of each of those places? Fresno apparently is at 308 feet above sea level. Death Valley is 282 feet below sea level, so negative 282. I had to look this up on Wikipedia. And then Shaver Lake, at some point in it, I guess they do like at the city hall or whatever, probably, is 5,627 feet above sea level. So those are the elevations of all those places, and now I've made this places table. So the places and their elevations. And let's say I want to do math with these elevations, and I'd like to get them back, but I don't really want negative elevations. Like, that's not good for what I want to do right now. Pretend that that was true. Like, your math wouldn't work with negative values. And so if you ever have a negative elevation, like we do for Death Valley, surprisingly, let's just say I want to cut off anything that's negative, just make it 0. Let's do that. So let's make a function that cuts off a value at 0 so that we can apply it to all the elevations of our table. That's where I'm going with this example. So I'll make a function called cut off at 0. Oops, at 0. And then it takes one thing, the thing you want to maybe cut off at 0. Well, we'll call that thing val. And then how do you, like, you either want to get, like, if it was Shaver Lake, you want to give back the 5,627. You don't want to cut that off. It's just if it was negative, you cut it off. But Death Valley, negative 282, you want to turn that into 0. So the way that you can do that, one way at least, is with the max function. You could be like, take the max of 0 and whatever the value was, because if it's above 0, the val will be the result. And if it's below 0, 0 is bigger than it. So return that result. Return the result of maximizing either 0 or value. The result of the maximum of 0 or that value that you passed. And I'll just omit a doc string because I'm lazy right now. So there's a function. And I can call that with a few different values. If I say cut off at 0, negative 5, and I'll just show you a bunch of things with commas. Cut off at 0, 0, and then cut off at 0, 42, to kind of show you how this works. These first two, well, 0 is the same. It doesn't really have the max of 0 and 0 is 0 either way. But negative 5, that one will be cut off and it will give back 0, because the maximum of 0 and negative 5 is 0. It's the bigger thing. And then cut off at 0 and 42, anything above 0 is just going to be that thing, because the maximum of 0 and 42 is the thing that was bigger than 0, right? So that's cool. And now let's do that. Let's apply this function to the elevation part of our table called places. And the way we do that is you say its name, and you say dot apply. So I've got places, dot apply. And then you say the function, the name of the function that you want to apply to the rows of this table. It's called cut off at 0. So that's the first thing. And then cut off at 0 takes one value, and you're going to run it on each row of the table. I want to run it on the elevation parts. Elevation is the one input to this function, so that's what I put here. I put the label of the one column, in this case, that I want to pass for each row of the function. Like, turn each row into its elevation, because it's the elevation value that I want to give as input, the one input to this function. So that's how you say it, and it will give you back an array of this function applied to every row of the table, all the elevation values, because that's what you chose to pick out. And so now I get 308, 0, 5,627. All right. Does that make enough sense for what this dot apply is doing? You got your table, you're applying it to every row of it. Here's the function I want to apply, and here's the input for each row. Use the elevation. Make that the val. That's my one input. And so it'll give me back an array of all the results. One for every row of the table. And because there's one for every row of the table, I can totally put this resulting value, this resulting array, back in the table. I can make it a new column. I could say places with a new column called, like, cut off elevation. And I can put this resulting thing right here into it. And so now I can have, like, maybe I can do some work with the real elevations. Like, I've got some programs that are okay with that. But maybe I've got a program that's not okay with negative elevations. I can give them the cutoff ones instead now. That's useful. That's useful and fun. And yeah, it's kind of weird. I didn't really tell you that it's weird, but if you're coming from another programming language, it's kind of weird to just say the name of the function by itself. That's totally normal, though. That's a thing. Like, it's just a name, honestly. Cut off at 0 is just a name. If I said shift enter with the name of the function, Python knows what it is. It's just like, it's a function. I can't print it out to you in any normal way. It's saved in memory. It's like, think of a box called cut off at 0 with code inside of it, kind of. That's what it's doing. But it really is just a variable name that you're able to call. That's all cut off at 0 is. It's a function. That's all a function is. It's a variable name that you can call with the parentheses. So that means you can assign it. weirdly enough. Like, you can give it a short name. Like, all right, I want to call cutoff at 0. Instead of cutoff at 0, let's call it cut. I can say this. I can say store this into this variable because they're just values that are in variables. And so now I've got 2 names for the function the second I run this line. Does that make sense? I've got 2 names for it, which makes like I place this value, whatever that is, the idea of the function, into this variable too. It's also there now. And so I could say cut of -5. Now it exists because it's just calling the other one. Isn't that fun? And of course, the other one still exists. It's still there. Cut off at 0, 42. They're happy. But that's weird and different and cool. They're just variables at the end of the day. You could reassign them, make them shorter if you wanted to. Like this is still linking back because we've given it another name. It's still linking back to this code, to this function. So I think that's everything all at once that I wanted to show to you. Any questions about that example? It's a little weird, but it will grow on us. We're going to need this idea, especially of applying functions to every row of the table that we're working with. All right. I have, let's see, one last thing I want to show you, and I want you to try it this time. So give this a try. I'll give you this final version of our percents function, because I think that's a good starting point. But I have a question for you now. So you don't have to include any data sets, because you can just call it. But here's my question for you. Try to make a function called calculate total, and it's going to take like a subtotal, a price, and then the rate of taxes for whatever county you're in. And so I want you to use that tax rate and the price you're given to find the final total of your input after tax. So for example, if the user wants to call your function calculate total, they might be able to pass, or they might want to pass. Maybe the price of the thing they're trying to buy is $5.99. They'll pass that for price, and then for tax rate, what is the Fresno tax rate? Does anybody remember? What's our sales tax? I don't think that's normal. Fresno City. Is it 8.975 right now? I don't know. It says 8.35 here. I guess it changes every year too. 2026. Why is it reloading? It won't let me type. There. Approximately 8.35%. Sure. That would make sense. Is that true? Fresno. Okay, we got 8.35. That's apparently our tax rate right now. Cool. So they could be like $5.99, then it would be 8.35 here. And then I want you to use your function to give back. Well, how do you do this? It's going to be what? $5.99 times whatever the tax rate was, and like done in the right way, time 0.0835. And then you got to add back the original price, because this is just like the tax amount, and then plus $5.99. Maybe round it to the nearest 2, because like you can only have cents, like something like that. That's one way to calculate the total for a certain value. And this is like a useful function, right? Because like you put this on like a checkout stands program. That would be something that somebody implemented somewhere. It's called calculate total. And so here's like a scaffold, a template, an idea for how we did the percents one. But I want you to make a calculate total function that takes 2 things. Give that a try. Any questions about the question? You don't have to write this down anymore, but I want you to like code it up if you can. Open up Jupyter, say def calculate total, right? And let's see if you can get it working. You can make 8.35 the default for the tax rate, so you don't have to give it. Like, assume we're in Fresno. But if we go to Madera, let the user still have the option of entering new tax rates for the decimal places. So yeah, take a few minutes to play around with that and ask me questions. But it will be satisfying to get it working on your own first, I think. I'll give you a few minutes to try that. Yeah, yell at me if you have any questions while you're trying it. Good. Another minute or so to try, and then I'll show you my answer. It was very loud. All right. Did any questions come up as we were trying it? Were we able to get it working? I give you back a final answer. Return back the price times the tax rate in the weird way, right? Doing everything right? So I'm about to give away the answer. I want to make sure you're ready for that. Dun, dun, dun. All right, let's do it. We're calling it calculate. This is the signature of the function, technically. That's how we say that. So I just say def, all that. Def, calculate total with a price and a tax rate. You've given those things to me. I want to do some stuff. We'll do that later. But like the whole point of it is that I can call it, right? I can say calculate total. Here's how I want to be able to call it. I want to be like, all right, I've bought something that's, I don't know, $5.99, and there's an 8.35% tax rate in Fresno County right now at the moment, apparently. Like, I want to be able to run that one. I also want to be able to run it with other prices and other tax rates. That's the whole point. Just have something called this that lets me do what I want. So like maybe I buy something that's $7.99, and I go to somewhere that there's more tax, 8.75 or something. I don't know. Like, those are the ways I want to run the function. Let's make it happen and return back the right answer. So yeah, how do I want to do this? Let's say, well, you can do it all in one line if you want. Return. It's going to be, well, return the tax. The tax part of the price is you take the price and you multiply by the tax rate, but the tax rate is in percents. And so if we want to do actual math with a percentage, we have to make it divided by 100. That turns like the 8.35 into 0.0835. And then that will actually, like this multiplication will give us the tax amount. Then we add back in the original value, the original price. So all that, plus the original price, that's the final answer. And I get these values. Those are the new final total plus tax for each of those values. Does that make no sense? Questions about that? Because I want to make it better. I want to round it. You see how you could do that? You could make it all in one giant return line if you wanted to, but you could also split it up. You could also be like, no, I want to make this cleaner. Let's save this and save the intermediate steps. Let's be like, all right, like the result value is do all the math, but I don't just want to return the result. I want to return a rounded version of that final result. So we'll say round it to 2 decimal places because that's how currency works in the US. And so now we get these answers instead. And it looks a little bit cleaner because I put it on multiple lines. I could have put this all on one line. I could have been like, do all this in the call to round and then comma 2, but that gets kind of ugly and hard to read. So it's important when you're programming to be able to write code that you can come back to later and understand what you're doing. So split it up when you can is my advice there. But I think that's what I wanted to say. Any questions about my answer for this? If you wanted to have a default tax rate, you can put that here, like 8.35 is the default. Now you don't need to give a tax rate if you wanted to do that in that way. That would totally work. I like that. But yeah, I think that is a good example, and I hope you're able to get that. Any questions before I move on to using functions, applying them to other ideas? All right, so let's predict the future. All right, this is a cool thing that we could use a function for. So let's look into our crystal ball and predict something. We've got some data sets. I showed you one before of heights of children. I think I showed you, I've got another one just for sons, but I've got heights of children as a data set and also the heights of their parents. So every row of the table I'm about to include is going to have like the height of the mom, the height of the dad, and the height of the child. And usually, with taller parents, there's taller children. And so we can kind of somewhat predict the height of a child if they're just still young. We can predict usually how tall they're going to be within a certain range. And so that's what I'd like to do right now. So let me include the table and I'll talk about the stuff in that next bullet that's in bold. But I want to do some prediction right now. Predict the future. So I've got a table called family heights. Table, if you'd like to include that too, it's here. It's in my data folder. It's called familyheights.csv. And I want to call that family underscore heights. But there's also a piece of that table that I don't want right now. It's called mid-parent height. I want to deal with that myself. So I'm going to drop that one. I'm going to drop column number 3 right as I include it. So it's not there. We're going to do that one ourselves. All right, because that's more educational. So here's my family heights table that I want to use. Get rid of that original column number 3. I don't care about it. We'll make it ourselves. So yeah, here is just a bunch of data. So like this is like the ID of the family, like family ID number 1, family ID number 2, just to know who is part of what. But you've got father's height in inches, mother's height in inches, the number of children they had, and like the order of the children, child number 1, number 2, number 3, the sex of the child, and then the height of that child when they were an adult, I assume, maybe at age 18 or 25, whenever they're done growing, I'm not sure. But they took that data, and we'd like to use this data. There's almost 1,000 rows with a bunch of families and their children and their heights and things. We'd like to use this to predict. Let's say you've got you're a doctor, you're a pediatrician, you've got a parent, 2 parents that come in, they're about to have a child. You would like to use this data of all these other parents and the heights of their children to predict that height of their future child, right? So that's what we'd like to do right now. So let's make that happen. The goal and the way that we're going to do it is like we are imagining that we're being given the heights of the mom and the dad for a child, we have no clue how tall they're going to be, right? That's the whole point of prediction. We have the father's height and the mother's height, but not the child's height yet. We're trying to use this data of stuff that we have values for to predict things that we don't have values for, right? So here's the key. We're gonna, all right, given some family, the heights of the mom and the dad that we haven't seen them before, they just walked into the clinic or something. We'd like to use the data that we have for similar parent heights. So if the mom and dad are both like 6 feet tall, then we're gonna go and find in our data set all the parents that are around 6 feet tall together and see how tall their children were, and use that to predict the height of the new child that we haven't seen yet, that we're not sure what they're going to grow up to be, right? How tall they're going to be. And that makes sense, right? We want to use data that's similar to predict the future, right? That's our goal. So we're going to take the average. Our goal is, let's just average together the heights of the parents that are close to the height of the parents that we don't know how tall their child's going to be yet, all right? And so I know that's a lot of words. I want to show you an example and it will help. Okay. But let's get one value for the heights of the parents by taking the average of the mom's height and the dad's height. All right. Let's call that the averages of our parents. So let's do the way that we can get the average heights for our children, for the parents, is you take the father column and the mother column and you just average them together, right? So we'll say it's family heights dot column father, add that to family heights column mother, right? And then divide by 2, using parentheses as necessary. So I got to put those in parentheses and then divide by 2. So this is going to be the average height of the father and mother for all of the children, or for all the rows in this table. This is the average father-mother height for the first 4 rows. It's all the same because it's the same family. And so those are the parent averages. All right. And that's kind of the table I want to make right now. I want that's all I really need. I want to use the parent average height and then the child height to do some predictions, all right? So let's make a brand new table called just heights. And let's make it start off as a blank table. Blank table, and here's the columns I want to put in. I want to put the parent average height, and that's the one I just calculated. That's in my parent averages variable. And then I also want to put the height of each child for that parent. And it's just going to be the same. Take this child height column all over again and shove it into this new table I'm making. That's family heights dot column child height. And so the very first row in my heights table is going to have a parent average of 72.75 and then a child height of 73.2. I'm just like putting those back in the right order, okay? But I'm making the table from scratch like this. And so here's my heights table. So now instead of like father height, mother height, I've got the parent average height and then the child height. And I'd like to use the parent average to predict the height of a child I've never seen before by using this data for comparison purposes. Okay, that's my goal, and let's go with that now. So we can make a cool picture to show what's going on here. I can do a scatter plot, right? Because this is my heights table. I can say heights dot scatter on using the parent average as the x-axis. And you do kind of see that there is a decent trend. It's not perfect because there's other factors that control how tall a child becomes, but you can see that as the parent average height gets bigger, so does the child height. You kind of see there's a line that could be drawn in here. It's a little fuzzy because it's not perfect. There's other things like, I don't know, where you live, stuff like that, I assume, controls how tall you become. But usually, sometimes, the height of your parents helps, okay? So you see that it's getting bigger. The child height is a little bit larger for parents that have a larger average height, okay? So let's say, this is our data. What I'd like to do is let's pretend we work at a clinic or something and the parents came in and they want to know how tall their child's going to be. So we take the father's height, we take the mother's height. They're about to have a kid. We don't know how tall they're going to be yet. But let's say that their average height was 66 inches, all right? The average height of the parents was 66 inches. We don't know how tall their child's going to be yet because the child still has a bit more. But what we can do using this data, I hope you see, is let's take all the people around 66 inches, right? Take all all the child heights for the parents around 66 inches, that's these guys, and maybe average them together to be like in the middle here. That would be a decent prediction of their child's height, their future child's height. Does that make sense? Given the past, predict the future. That's like a good estimate. And so let's just do that for that one family, and then we'll try to program that as one big function. So that's my goal. Like, use the data we have for similar parent heights to predict the child height. So we've got a brand new parent set of parents coming in. They want to know how tall their child might be. And so we know that their average height is 66 inches, let's say. Let's pretend. So let's go find all of the parents in our data set that have that an average height of around 66 inches. Like where the parent average values are between, let's say, between like 65.5 and 66.5, like around an inch around 66. Okay? So those are all the rows in the table. Oops, I put too many parentheses. No, I didn't. Is that fine? Sorry, it's heights. So here's all the rows in the table with parent averages around 66 inches. And then, so that's all these guys kind of. So I've got that table. It's like everybody around here. And let's use all their child heights that we actually have data on. Let's average them all together to get a good estimate for how tall this future child might be. So these are all the children that are close to 66. These are all the children of parents that are who have a parent average of close to 66 inches. Close to 66. So that's that table. And then what I'd like to do is like give back a range, right? Or I can give back an average. I can also give back a range, like what's the smallest, like what's the shortest child that it might be, like this guy, like what's the tallest it could be. Like that's a useful value too to give back to the parents. Like, all right, we've got data that sometimes your child can be this short, they can sometimes be that tall. Because maybe it's the grandparents that was controlling this, who knows? But parent average is a good enough predictor. But you can be like, all right, look at all these child heights now. Go to the child column, close to 66 child column. These are the children of parents whose heights on average were close to 66 inches. And then we'd be like, what's the minimum that we see here? It's apparently 57.5 inches. What's the maximum that we see here? 73.5 inches. Do you see how that's already a good thing? Like that's already data that we can give back to the parents and be like, all right, this is kind of the range for things that we've seen in the real world of how tall your child might be. Don't expect your child to be 80 inches tall. Don't expect your child to be 50 inches tall. They'll probably be between this guy and this guy, most likely. That's what we've seen. That's useful already, right? You could also take the average of all these values and be like, that's my prediction. That's like right in the center. That's kind of what you can expect your child to be on average, their height. And that's, you can say np.average to take the average of a column, because that's an array. Like take this whole thing, np.average, all that. And you can be like, all right, we kind of expect your child to be within this range, but probably they'll end up about that tall, which is a little bit taller than the parents' average, interestingly enough. And so I know that there's more to it. There's like male versus female. There's like how tall were the grandparents. But there's still a trend, and we're exploring that trend with this data. We could go further if we wanted to, if we took more data. But this is cool. This is prediction, and this is data science. I love that. Are there any questions about what I just did and how I made this prediction? Because I'd like to generalize this for like, you give me the height of a parent, I will predict their child's height. Like that could be a function now. Right? That can be a function. Let's make that function. We'll be like, all right, we'll call it predict child height. Predict child, maybe. Predict child. You give me the average parent height. I'll call that P average. Give me the average parent height. And what I'm going to do is all these things, but I won't just say, I won't hard code these numbers anymore. So like, all right, instead of close to 66, it's like close to whatever the parent average was. These are the close points. It's where the parent average values are between like P average minus half an inch and P average plus half an inch, whatever you gave me, right? And then what do I give back? I want to give back like the average of this close table that I just made here. It's not called close to 66 anymore. It's called close points. Give me the average for all the children there that I've seen, and that's what I return back. And so now I can call that function, predict child with 66 inches, and I'm going to get back the same exact answer because it's doing the same work, but now it's generalized. Are there any questions about what I just did to make that function? Just copy and paste the things and generalize them. You give me a parent average. Let's go find the children or go find the parents in my original table around that height, around that average height. Take the children of all of them and give me their average and give that back. Isn't that fun? Now you can predict anything. All right, if you've got a parent average height of 70 inches, let's say that their child's going to be about this. They'll be, on average, about a little less than their parents sometimes, because 70 is, I guess, taller than usual. So that's kind of fun to think about. Are there any questions about how we made that function? It's very cool. It's very fancy. All right. Let's see. What else do I want to do? Yeah, so now for because I've got this heights table, right? You better believe I can see how good my predictions were for every child. Like let's take, all right, here's the parent average. I can use my function on 72.75 to create an average or to create a prediction for the child's height. And I also know what this child's height eventually really was. Let's add the prediction to this column, or let's add the prediction as a column to this table. So I'll make like a heights with predictions table. Like take the heights table, add a new column of me like making a prediction for every child. And how do I make that prediction? I take all these parent averages and call my function, right? The way I do that is I say, let me do it down here really quick. It's heights dot apply, right? Apply my function, which is called predict child, to every row where the input to the function is the values in the parent average column. So parent average are the inputs to my predict child function. And this is going to then make a very long, heights. I always get it wrong. This is going to make for me a very long table. It's going to do a lot of work, so it took a while. But here's my predictions for every one of those children with their parents' average for that table. So that's what I want to put as a column here. Prediction is that. I hope that makes sense. And then like that's my new table with the heights, the original heights, and then my predicted height as well. Get rid of that. So my prediction is sometimes decently close. Look at all these where it's pretty darn close for this to what the child ended up being. It's like it's an average. It's usually pretty good. But sometimes it's a little below. Sometimes it's a little above. But on average, it's kind of in between because like the children of these parents, right? It was like a couple of them were above the 71-inch average. A few of them were below the 71-inch average. So it's never a perfect game to be playing, but it's very close, right? It's a prediction. And so a cool thing that I can do now is scatter plot this. So heights with predictions dot scatter, where parent average is on the X and the other two are on the Y. And so now I've got like a little trend line going on. Here's what our function predicted for a height 66 parent average. That's our prediction. And you see that that's kind of smack in the middle of all the options for height 66 parents. And so this is our prediction for every height. The yellow dots are the prediction that we're creating, giving back to the parents. And you see that's kind of following the trend of the graph, which is really cool. Are there any questions about that? Do you see what we're doing there? See how I made this table where I applied our function to every child height to see how good our predictions were. But this is the meat right here. That predict child function is very powerful. Go find me, can you read it? Go find me all the parents that have a similar height to this input height, around there, plus or minus half an inch. And then give me the average of those children, those ones that we know about. We can use that to predict the height of a child we've never seen before, that hasn't grown up yet. That's so fun. That's very powerful. I like that. So yeah, if we're good, I just want to show you one more thing and then we can practice it. It's that dot group operation. I want to actually explain that to you. So dot group. Let's go there. Let's talk about the documentation, and that can be one of the last things we do today. So dot group works like this. You got a table and you say dot group, and then you give either one column or a bunch of columns, and then you can potentially give a function. And I'll talk about those. By default, if you say dot group, you can just give a label, and it will break down your table into all the different values of this column's data and it will count how many appear multiple times. Kind of. It will give you back the counts of things. So that's what dot group does. You group by like the kind of thing, group by type. It defaults to counting, but you could default to other things. And so let me show that to you. All right, I'll try to explain it. Dun, dun, dun. So I want to make a new little section here. I'm pressing buttons. Grouping. So here, let's input our ice cream cones table, a nice small table to practice with. So here's my ice cream cone table, and dot group kind of works like this. I can say group all the cones for me by their flavor. So it'll take the flavor column, and you see how there's a few chocolates? There's a couple strawberries. By default, it's going to bring them all together. It'll find all the bubble gums, it'll find all the chocolates, it'll find all the strawberries, and it kind of makes a array of all those things, and it gives you back the length of that array. So like there was one bubble gum by default, and it gives you back the length. So there were 3 chocolates. It shows you that. By default, it counts them. There are 2 strawberries. There was 1 vanilla. But secretly what's going on, whenever you say dot group, is it's bringing everything together, all the rows together on that column that you're saying. It's bringing them all together. So like for chocolate, it brought together this row and this row, everything with a chocolate as a flavor. It also brought together this row. And so they're all together at once as an array. And then it just, by default, took the length of that resulting array. Okay? So if you didn't want the length, you could apply any function to that combined array of things that you got. By default, it says it's just doing that. So it's giving back the length of all those values. How many colors were there? How many prices were there? 3. So it's kind of doing this and shrinking it down, if you want to think about it that way. But you could say how you wanted those values that it brought together, that it grouped together, to be combined. All right. So the default was give me how long they were. You could say show them all to me, create an array of all of them to me. This list is a function that combines values, kind of like make array. So consider this to be mostly the same as make array. I'll talk about lists more later. Mostly the same as make array. But you can start applying weird stuff. You can say sum together all the values that I see now. And that's where it starts getting powerful. Average together all the ideas that I see now. That's when it gets kind of cool. So instead of saying like len and all that, just say, let me get rid of this. So by default, it groups by flavor. It brings all the chocolates together. And then you could run a function on all those chocolates at once. By default, it's just showing you how many there were. Give me the length of all those things that were brought together. But you could say, no, hey, group by flavor. And then for all of those things that you've brought together, all the chocolates that you've brought together, all the strawberries that you've brought together, apply the average function to each of those columns that you've brought together. So this is what is now happening. It's brought together all the chocolates. It tries to take the average of each of the remaining columns, so color and price. It's impossible to average together colors. Those are just strings. That makes no sense. But it's totally possible to average together prices. And so you see nothing for color average, but price average makes sense and exists. What it's done is it's brought together all the chocolates, and it's done an average of all the prices for every chocolate. Does that make sense what it's done there? That's very powerful. So it's bringing together all the things that you're grouping by, and then it's applying whatever you provide here to each column if it can. So like the average chocolate price was a little over $5.08. The average strawberry price was $4.40. The average vanilla price, there was only one. It was $3.50. That's really cool. So it's bringing them all together and it's showing you things. Does that make enough sense? And you can control what it's doing to those things as it brings them together. It's combined them wherever the flavors were the same. Give me all the chocolates. It brought them all together, took the average of their prices. That's so powerful. So yeah, by default, it's kind of like bringing them all together, giving the length of all the things it's brought together. So there's that. Yeah, len is kind of the default, what you're getting. List just kind of gives you back the array itself. Make a list out of it all. And so here's like, it's brought together all the chocolates. Here is the list of all of the different values for color. It was light brown, dark brown, dark brown. Here is the list of all of their prices, $4.75, $5.25, $5.25. And so that's like, give me the list back, give me the average of all those things. So if the average, you can kind of see it as like, all right, it took all these values that it brought together and it averaged them. That's what it's doing. That's really cool. You can do the sum. Another idea is the sum, right? Sum's very similar to an average. So like, all right, group by all the flavors, bring them all together, and then sum up all the things you see. Again, it's impossible to sum up words as colors, but prices you can totally sum up. So chocolate, it brought all the chocolates together, and it added up their prices. So it took all these guys. It's easy to see it when you made it lists, but it added up their prices into $15.25. That's cool. All the strawberries, there were 2 of them, so it added up their prices into $8.80. Nice. And so you can do some really cool things and make fun stuff happen, and that is kind of what grouping lets you do. It's here's kind of things that you could do and ask questions about. You could be like, first of all, if you don't want to see the color, just get the rows that you want right now. Here's cones. I want to do stuff with flavor. I want to group by flavors and deal with prices right now because I can't really do math on colors. Can't take the average of a color. You can be like drop. Cones dot drop the color column. And now when you do dot group, it's going to give you the price. It's going to bring together only the prices because that's all the flex now. So, all right, drop the color, group on flavor. And then what do I want to do with every flavor? Maybe you can be like, show me the maximum price. I got a lot of money. I want to see the maximum price cone for every flavor. So this is applying the max function after it's bringing together all the chocolate cones. And saying, all right, the maximum chocolate cone that exists is $5.25. The maximum strawberry cone that exists is $5.25. There are others, right? There was a cheaper chocolate cone, but that's going away. We've brought them all together. We're aggregating them. That's the fancy word. We're aggregating them by the max function now. That's what we're applying as we brought them together. So that's what grouping lets you do. By default, it's counting how many things are like, they were all chocolates. How many chocolates were there? But you can also apply functions to the things to all the chocolates that have been brought together. And you can apply those functions to each of the columns that remain. And that is very, very powerful and very cool. Cool. I think that's what I wanted to say. Any questions about dot group? Do you kind of see it? So usually you'd just like use the default, get the counts, or like a lot of the times you'd want to get the average or something like that. So that's a good one to remember. And so here's a good way to practice. I have a question for you. Boop. Here's the dot group example for the cones. Try to do the same for Pokemon. All right, read in the Pokemon table. Try to get the average HP hit points, like that's how much damage a Pokemon can take. Get the average HP for Pokemon after you've grouped them by their primary type, which is called type 1 in the table. So like get all the electric Pokemon together, like Pikachu. Get all the fire Pokemon together and see how much damage they can take on average. Get their average HP values for all the electric Pokemon, all the fire Pokemon, all together. It's going to be a dot group. Does that make sense? So give that a try. You don't have to post your answer anyway, but I want you to try it. But try to get that result. It might make most sense to drop every column you don't care about because you'd see the average of a bunch of other things. You didn't do that. That's an idea. Try to read in that Pokemon table from our data folder. Average HP separated by types. Pokemon type. A couple minutes to try to show your mind and safety. And then once you have that resulting table, you can plot that now, can't you? Think about what kind of plot would be a good one. Look at the documentation pages to decide. And you've got a bunch of types and now averages of HP for Pokemon of those types. What kind of plot should you make to display that? And this is a great intro to like the way you'll be thinking, the kinds of things you're going to want to do as a data scientist. Here's how I want to explore the data, and here's the kind of visualization I want to make after I've explored it, or to help me explore it further. I'll give you a couple minutes to play around, then I'll do it too, and then we'll wrap up. And please let me know if you have any questions as you're trying it. I want to help before I just give it away. All right, that's my timer. You can look away if you're still working, but I want to answer your questions first if you have any. I want to group by the type 1 column, that's for sure. But yeah, please yell at me if you have any questions. I'm just going to import the table right now. That's the first bit. It's always necessary. Pokemon equals, let's read in that table. Data, Pokemon.csv. Alright, so here's every Pokemon. And there's a million columns, way too many. But we got type 1, the primary type of the Pokemon, as well as their HP of every Pokemon. I think it's at like level 50 what their HP is on average. It's here somewhere. It's just called HP lowercase. It's very hard to say. Very hard to find because it's so small. But that's all I want. I want type 1 and HP. Type 1 and HP. I can select out just those columns, and that's all I want to work on. So I can make a little smaller table for myself by doing that. Pokemon.select out just the type 1 column as well as the HP column. In that order is fine. Put the order you want as well. And so this is a much easier thing to do. I don't even care about their names anymore. But like, all right, the first 3 were grass, the second 3 were fire, and here were their average HPs at like level 50 or whatever. And so that's a start. Let's call that table, that smaller, easier to manage table, P. I'll call it P for short. And then what I want to do is I want to group, right? I want to group that table, P.group. Group by type 1. Right? Bring all the grasses together. Bring all the fire type Pokemon together. And then what do I want to do with it? I want to average all of the HPs. And there's a bunch of them. If I say list them all, like that, here's all the bugs. All the bug Pokemon there's a bunch of their HPs were all over the place. All the dark Pokemon had HPs all over the place. There are apparently only 3 flying type Pokemon as their primary type. That's interesting in itself. But you got a bunch of options there. But what I'd like to do is not just, don't list them out, but like do the average. Like bring them all together and then do the average, please. And so one way to do the average, it's a function called np.average. I think there's also np.mean, most likely. But let's do np.average. And this gives me the average. This is cool, right? This gives me the average HP for all of the Pokemon of every type. So it brought together all the bug Pokemon, and had all their HPs together at once, and it took the average. It brought all the electric Pokemon. It had all their HPs together at once, and it took the average of all of them. Does that make sense, what it's done? Questions about that? And then if we want to display this, we've got a categorical variable and some numbers to go along with it. That screams bar chart, right? That's a bar chart, and it looks cleaner when things are sorted. So let's sort these also just to know like what's the best type anyway. Let's sort all these by, it made a column called HP average. Let's sort that descending. Descending equals true. And now you kind of know why there's an equal sign there. There's a parameter that we're giving a value to. So it looks like dragon Pokemon, those are the strongest. You want to have a team of dragon Pokemon if you can. And then surprisingly, normal Pokemon are pretty good. Fairy, ground, psychic, dark, goes in that order. And so if we want to graph this, we can do a bar chart now. Take this resulting table, this whole big long thing, and then we can do dot bar H on the type 1, that's the categorical variable that we want to use, and then the remaining column, the HP average, will be what we show. And so here is our pretty graph based on that data that we just created and calculated. And you see just at a glance that unfortunately electric type Pokemon don't have a lot of HP. Maybe that just means they're impervious to a lot of attacks. I don't know. They did some stuff in the game to make it kind of fair at least. But I guess that goes to show that you don't want a team of bug type Pokemon because they're squishy and easy to defeat or something. But now you can see that visually. I guess is cool to think about. Yeah. So yeah, you want some dragon Pokemon on your team, not so much bug Pokemon, I guess. But yeah, I think that's a good example to show and talk about. Are there any questions about how I got this on the screen? It's definitely a fun example to study and try to do this yourself. Ask other questions and try to do some stuff with grouping involved. Yeah. So it was nice to make this smaller table for sure, because otherwise we'd be working with this giant Pokemon table and we get the average for like average all of these against fire, whatever that means, average defense, average capture rate, like all those things would appear if we did the group with the average, but it's faster this way. But if you just want to group, here's what would happen if we said dot group with by type 1 of the whole table and then do average. It would take the average of every single column that it could, which is disgusting. But if you just wanted to know how many Pokemon were of grass type, were of electric type, then the default of counting them all up for you is fine. You didn't have to make a smaller table for that because it just combines them all. There were 52 fire Pokemon. There were 39 electric Pokemon. That's nice. Okay. So yeah, that's kind of what I wanted to say about that example. I have one last thing to tell you about group that's really quick. Are there any questions before that? I want to show you how to group by multiple things, multiple combinations of values. So let's go back just one last time to our cones table for the day. And the documentation page on group is kind of hinting at what you can do. If column or columns is an array, it groups by each unique combination of elements in those columns. And that's what I want to show to you now. That's sometimes useful. So here's my cones table. What if it's not enough to group by the flavor? Cones.group by flavor was not enough. I wanted to group by something more fine-grained. Let's say I want to group by flavor and color. Bring all the ones that have the same flavor and color together. There's going to be more combinations, but do you see how there's 2 dark brown chocolates? Does that make sense? See, there's 2 dark brown chocolates, so there's that flavor-color combination exists twice in this table. I like to bring just those together and do something with them. I like to consider dark brown chocolate to be separate from light brown chocolate. And you can do that by grouping with an array. Make array of first group by flavor, then group by color. So make an array of all the labels that you want to group by in that order, and it will group by combinations, every combination of flavor and color. And by default, it gives you counts of things. So it shows me that there were 2 dark brown chocolates, there was 1 light brown chocolate, and then there were 2 pink strawberries and 1 of everything else. Do you see the difference there? It's done. It's grouping by both flavor and color at the same time. It's considering anything that has a different flavor or a different color to be separate. So light brown chocolate and dark brown chocolate are now different ideas to this grouping call. Completely different. Whereas if we just group by flavor, it brought together all the chocolates, the light brown and the dark brown, right? This is going to group by different things. More combinations, more fine grain there. And of course, by default, you get the count, but you could have done something else. You could still say what you want done when you've brought together all those things. Give me the minimum price. Call min on all the things that you've brought together. On those two dark brown chocolates, show me the minimum price of those. Like if I wanted that, how much am I forced to spend at a minimum? If I want a pink strawberry ice cream cone, there's two options. What's the minimum priced cone that I could get out of those two? Because there were two of them, right? That's still a thing. I think that's what I wanted to say. So you can group by multiple things at once, and it will group by every different combination of these label values. Every different combination of flavor and color together now. Okay, and it considers them separate. Even though like their flavor was the same, if their color is different, it's going to consider them as two different things. Okay, so it's separated the different kinds of chocolates. Interesting. But sometimes you want that ability. Any questions about that? Because that's the last thing I wanted to show you. I guess one thing I could tell you is sometimes people are lazy and they don't like to type make_array. If you just want to make a very quick sequence of things, it's not the same as an array, so you can't do NumPy stuff. But if you want to give them to one of these library functions, it's a little bit easier. You may have read about this in your book already. But if you just put your sequence between these angle brackets, these guys, those two just like that, it's square brackets. If you put them between the square brackets, it's almost the same as making an array. It's called a list. So I said that word a few times today because that's something you can do when you call a group. But this is a list of these labels. It's a little bit different than an array of the labels, but the data science library for this particular purpose doesn't care. And so it's a little bit quicker, and this will do the exact same thing. Okay? I think that's the last thing I wanted to show you. So I'll section off this for next time by doing a little line. But I think that's all that I wanted to say. So there was a lot of cool new stuff today. I guess the key idea is making a new function. All right? Making a brand new function. Now we know how. And that just opens up so many things for us, right? It lets us do some very complicated things by giving it a name. Now we can split up different ideas of different computations into functions, and that makes it easier for us to achieve our goals with data science. I like that. So I think that's where I want to leave us today. Are there any last questions that we want recorded before I let you work? All right.